Welcome to the next lecture of switching theory and logic design. In this class, we are going to discuss the topic of resistors. Okay, so actually we are discussing the fourth unit related topics. The fourth unit is nothing but as sequential circuits part 1, where the sequential circuits are nothing but as the output of the sequential circuits are completely depends on the present input and the previous output. This is the behavior of the sequential circuits. So, where coming to the sequential circuits, the concepts of sequential circuit we have already discussed in the previous videos. We have started from the latch. So we have seen the definition of latch and how the latch is working, and we have seen different types of latches, and we have continued that topic with the flip-flops. So after completion of the flip-flops, we have seen how to convert from one flip-flop to another flip-flop. That is also we have completed. Now in this class we are going to see the concept of resistors. Right? Let us continue. Right? Here actually there are two types of resistors are available. Actually there are two types of resistors are available. The first one is normal resistors and second one is shift resistors. So the first concept is resistors and second concept is shift resistors. So where the resistor is used for storing the data, where the shift register is used for storing the data and transferring the data from one place to another place. So that is about the shift register. Almost all for the both resistors we have the same operation. Next, first see what is the definition of resistor. What is a resistor? Where a resistor is containing of group of flip-flops. That means if you see the resistor, you have lot of flip-flops in that particular resistor. That is a group of flip-flops. Generally it is formed with the D flip-flops or SR flip-flops. Next, coming to that, resistor is a device to store multiple binary information data. Multiple binary information data. Right. So I said that the registers we are using for storing the data and shifting the data. For storing the data, we are giving the data in terms of binary. In terms of binary. Okay. In terms of binary. So here we see it's very simple. The register is storing the data in the binary form. Right. So for storing the binary data, we need flip-flops. So each flip-flop is stores a single bit of information. So flip-flop is a single bit storage device. And for increasing the memory, actually in the flip-flop we can place only one bit of data. For example, if you want to store 1000 bits of data, you need more amount of memory. That means you need nearly 1000 flip-flops. So for increasing memory, we need multiple flip-flops. So for n bit storage, we need n flip-flops. For example, if you want to store 1 KB data, then you need 1 KB flip-flops. If you want to store 1 MB data, you need 1 MB flip-flops. That means if you want to store 1000 bits or 10,000 bits or 1 lakh bits, you need the same amount of flip-flops to store the data. Generally, for storing this type of data, we are selecting the flip-flop as D flip-flop. So generally D flip-flop is we are using for storing the data. Next, coming to that, where the register is used. Generally, what are the applications of the register? So for computing operations, for storing operations, generally we are using this registers. First you see here, use it to perform simple data storage, movement, manipulation and processing operation. For example, load, increment, shift, add, etc. So when you take your computer or when you take your mobile, you have a processor in that. So the processor generally storing the data and it is computing the data and it is shifting the data. So in the place of processor, you have a particular memory called cache memory. So generally in the cache memory place, we are placing this flip-flops concept. That is the registers data, the registers memory concept we are using exactly at the particular of processor, or you can use at the place of RAM. In the present day, we are using the storage devices. In the place of HDD, we are using SSD, solid state devices. So most of the present day generation laptops are coming with SSD storage device. So for the SSD, for manufacturing the SSD devices, we need the flip-flops. Next, So next application, computer and data communication. So generally, almost all the computer application, it needs register memory, and for the data communication, for transferring the data from one place to another place, we need a communication channel. So that data communication is also completely dependent upon this data. Generally, when you are transferring the data, that data we are not storing, just we are using as a temporary storage element that particular data communication path. So see here, registers are used generally as a temporary storage in the processor. So in the processor, we are using the cache memory as a temporary storage device. So at that place, we are using this registers memory. Serial and parallel data communications. So when you are transferring the data either serially or parallelly, you need the temporary memory location. That temporary memory location is completely connected by using the registers. Next, coming to that. So the first register we are going to discuss the concept is buffer register. So register is nothing but as group of flip-flops, and it is used for the storing the data. What is meant by buffer? Buffer is nothing but as, if you are giving the 0, the output is also 0 for the buffer gate. If you are giving the 1 for the buffer gate, the output of the buffer gate is also 1. That means whatever the information you are giving here, for example, if you give the 0 for the buffer input, the output is 0. If you are giving the input is 1, output is 1. Like that, here we have the buffer register. We have the buffer register. It is very important. This type of configuration we are using as buffer register. So the register, it will take the data, whatever the data you are giving at the input side, the same data it is generating at the output side. So this is the generally called buffer register. Buffer register. So see here, first I am giving the data here in the form of D1, D2, D3, D4. So before that, see here, we are using for storing the data D flip-flop, where D flip-flop is acting as a data flip-flop. For the data flip-flop, when you are giving the 0, the output is 0. When you are giving the 1, the output is 1. So with the help of D flip-flop, we are constructing the buffer register. So here I am taking the 4-bit buffer register. So this is an example of 4-bit buffer register. So see here I am giving the data for this 4 D flip-flop. So for the first flip-flop I am giving with the representation of D1, and with the representation of D2 I am giving for the second flip-flop. With the representation of D3 I am giving the next D flip-flop input data, and D4 is the last flip-flop. So these are the data I am giving parallelly to the shift register. Next, coming to that, this is the 4 bits of data I am getting at the outputs. So see here, the D flip-flop has an output terminal called Q. So this is I am representing as Q1. This is I am representing as Q2. This is I am representing as Q3, and this is I am representing as Q4. So see here the data we are giving at the input side as D1, D2, D3, D4, and I am collecting the data at the place of outputs Q1, Q2, Q3, Q4. Okay, so now I have a common clock signal for the all registers. So see here I have connected a clock signal to the first flip-flop, second flip-flop, third flip-flop, fourth flip-flop. All 4 flip-flops are connected to a single clock signal. So here, whatever the data you want to store, first you will have to write here. So for example, I am storing the data 1001. Now I want to store the data 1001. Now put the values at the D1 is equal to 1, D2 is equal to 0, D3 is equal to 0, D4 is equal to 1. So you are giving the data parallelly, so you can give the total data to here. Now you have to give the clock pulse. So when you are giving the clock pulse, automatically the inputs are processed to the output. So here I am giving the clock pulse as positive edge triggered. So here I am giving positive edge triggered clock pulse. Now this D1, whatever the input is available here, the same input is transferred to the output. Now Q1 output is equal to 1, Q2 output is equal to 0, Q3 output is equal to 0, and Q4 output is equal to 1. So the output simply follows the input. The output simply follows the input. So whatever the input data here we have, the same data is went to the output. So this is the a basic buffer register. So the basic buffer register, it is acting as the data storage device. So whatever the data you are giving at the input side, the same data is followed to the output whenever you are giving the clock pulse. It's very simple thing. So you have to understand the concept. So whenever you are giving the data, the output is following the same as is the input data. but with the help of clock bus. When you are given the clock bus, the input data is going to the output. So this is the buffer register. Now, next coming to that, the most important concept, controlled buffer register. Next concept is controlled buffer register. So coming to this controlled buffer register, what it is doing? Okay, what is the purpose of controlled buffer register? So I said that buffer register just whatever the data you are giving at the input side, the same data you are collecting at the output side. Okay, so the same data you are transferring, but here we have added a special word called controlled. Okay, so here the controlled is very, very important. Here we are taking the control signal as a load signal. So the load is a special type of signal. It is used to store the bits into the flip-flops. So here we are using the load signal to store the data. Here we have the same as is input, same as is outputs, but we are taking the permission from the load. Here we are taking the permission from the load. That is, a load is a supervisor, or a load signal is the instructor. So here the load signal is very important, right? Whenever the load is equal to 1, the input data is going to the output. So see here, Q1, Q2, Q3, Q4. These 4 are the output signals. So remember, these 4 are the output signals. Okay, so whenever the load is equal to 1, the output follows the input. So here I am giving input signals are X1, X2, X3, X4. So previously we have used terms A, B, C, D. Now I am giving the input signals are X1, X2, X3, X4. So the same input signals are present at the output. So when I have not given the load signal, so I am not giving the load signal, so then the output of the particular register is previous output. So whatever the previous output is there, the same output will be available when you are giving the load signal value is equal to logic 0. Okay, it is very simple. Now coming to the operation, here we have a clear signal and here we have a clock signal, here we have a load signal. So the clear signal, so whenever you are giving the clear signal, actually this clear signal is the active low signal. Here the clear signal is the active low signal. So the clear signal we are representing with clear bar. Clear bar, we are representing with clear bar. So when you are giving the clear bar, so see here, so the clear bar signal is equal to 0. That means the complete flip-flops are going to the 0. The output of the flip-flops are 0, 0, 0. Here we have 4 zeros. So when you are giving the clear value is equal to 0, then all flip-flops are representing the output as 4 zeros. So when you are giving the clear 1, so here the clear is not working. Here the clear is not working. How? That I will see in the next slide. Now coming to here, so whenever the clock signal is there, it will check the load value. If the load value is equal to 1, then the output of the register is equal to inputs, otherwise the previous output. Now we will see the explanation related diagram, right? So this is the controlled buffer register. Okay, let us see this picture. First we will understand what is this picture, right? Here we have 4 flip-flops. So this is the first flip-flop, this is the second flip-flop, and this is the third flip-flop, and here we have the fourth flip-flop. So totally here we have 4 flip-flops. This is the first step. Next, for this flip-flop, we have a clock signal. So that clock signal, we have a single clock input signal. We have a single input clock signal. So when you are giving the clock pulse, automatically the 4 flip-flops are going to the working condition. So this is the clock signal. Next, clear signal. So see this clear signal. This clear signal is connected to the D flip-flop by using a bubble. This clear signal is connected to this flip-flop by using a bubble. For all the 4 flip-flops are connected to the clear signal with a bubble. Okay, that means whenever the clear value is equal to 0, then only the flip-flops are going to work. So whenever the clear value is equal to 1, here the clear signal you are not giving to the particular D flip-flops. Actually clear signal we are using for the resetting the flip-flops or resetting the register, right? So when you are giving the clear signal, automatically the output of the D flip-flop is equal to 0. It is not related to the clock signal. So see here, the clock signal and the input signals, these all are called synchronous signals, where clear, reset, preset. These three inputs are asynchronous inputs. So when you are giving these inputs, so whatever the clock signals, whatever the input signals, they won't work. They won't work when you are giving the clear, preset, reset. So here I am writing again. So see here. So clear, reset, right? These three signals, right? These three signals are called asynchronous inputs. Clear, reset, preset. These three are called asynchronous inputs. These asynchronous inputs are independent of the other inputs. There is no relation with the load and clock signal. Okay, these three are the asynchronous signals. Okay, these three are the asynchronous signals. And coming to that clock, it is a synchronous signal. Clock and inputs are the synchronous signals. So mainly you have to remember clock is a synchronous signal and clear, reset, preset are the asynchronous signals. Right. Now coming to here. So when you are giving the clear, the remaining inputs, otherwise the remaining outputs are we are not considering anything. So when you are giving the clear input as 0, automatically the outputs of the clear output of all the flip-flops are going to be 0. So when you are giving the clear is equal to 1, then the flip-flops are not bothering about the clear input. Why? Because at that time the remaining inputs are going to work here. Okay, so whenever the clear is equal to 1, then only the clock pulse is working, then only the inputs we are giving to the flip-flops, right? So here we are using a common clock signal. Okay, right. Now coming to here. So before giving to the clock signal, so what are the extra connections are available for this D flip-flop? So see here, the D input is nothing but as output of this AND and OR gates combination. All the D flip-flop inputs is the combination of AND and OR gate combinations, right? Coming to that, additional inputs. So here we have the load signal. Here we have a load signal. So whenever the load signal is equal to 1, then it will take the input data to store or to process to the output. Okay, so whenever the load signal is equal to 0, then it should work like the previous output it has to show again at the place of output. That means the previous output is present output. Like that we have to work. Next, coming to see here, x1, x2, x3, x4. Here we have totally 4 signals. That is x1, x2, x3, x4. These are the input signals. It is nothing but as D1, D2, D3, D4. x1, x2, x3, x4 are nothing but as D1, D2, D3, D4. Okay, these are the original input signals. Now coming to here, the load signal. Here we have the load signal. So when you have used here a NOT gate, here you have load bar. This is the load bar signal. This is the load signal. Here you have two horizontal lines. One is representing load bar. The upper one is representing the load bar. The lower one is representing the load signal. And the load signal is connected to this first AND gate, and second AND gate, third AND gate, and fourth AND gates. So here for the AND gates, one input. So see here blue color. Here I represented total 4 blue color AND gates. These 4 blue color AND gates, 1, 2, 3, 4 AND gates. One of the input is connected to the load signal, and next 5, 6, 7, 8. This pink color AND gates. For this pink color AND gates, one input connected to the load bar. One input connected to the load bar. And coming to here, first for this blue color. For this blue color AND gate, one input is equal to load, and second input is equal to x1. Okay, for the second AND gate, one input is equal to load and another input is equal to x2. And the third AND gate, one input is equal to load and another input is equal to x3. Like fourth AND gate, one is x4 and another one is load. For the blue color AND gates. Next, coming to that, this pink color AND gates. For the pink color AND gates, so one input is equal to load bar. One input is equal to load bar. One input is equal to this load bar line, which is connected through the NOT gate. Next, another input. See here, the another input of the pink color AND gate. So 5, 6, 7, 8. So another input is equal to output of the first flip-flop. For first AND gate input. So the first fifth AND gate, one of the input is connected to the first flip-flop output. The second flip-flop output is connected to the second AND gate input. Like that we have connected. So the AND gate, the pink color represented AND gates 5, 6, 7, 8. For this 4 input AND gates, one input is connected to the load bar, another input is connected to the same flip-flop output. Same flip-flop output. Now we have to start the operation. Now we have to start the operation. Right. Coming to that operation. So when you are giving load 1, so see here, this complete line is going to 1. This complete line is going to 1 and this complete line is going to 0. This complete line is going to 0. So we know that the AND gate operation, if any one of the input signal is equal to 0, automatically the AND gate output goes to 0. Now the first line, upper one line is the 0 value and the lower one value is lower line value is equal to 1. So here for the blue color, one of the input is equal to 1 and this pink color, one of the input is equal to 0. So here for all the pink color AND gates, one of the input is equal to 0. Automatically, if one of the input is equal to 0, the AND gate output is equal to 0. Now this AND gate output 0, this AND gate output 0, this AND gate output 0, this AND gate output is equal to 0 over. Okay, right. Now here pink color AND gates are in not working condition. So when you are giving load is equal to 1, the pink color gates are not in working condition. Remember, when you are giving load is equal to 1, then the pink color gates are not in working condition. Now coming to the blue color. So one input is equal to 1, it is over. Another input is equal to x1. Another input is equal to x1. So now see clearly, whenever x1 is equal to 1, both inputs are 1 and output also will get 1. If the x1 is equal to 0, so see here, one input here it is equal to x1 and one input already we made 1. So here x1 is equal to 0, output is 0. If x1 is equal to 1, output is equal to 1. So the x1 as it is follows to the AND gate output. So here the output is equal to x1. If x1 is equal to 0, both inputs are 0. For the OR gate, the output is equal to 0. If x1 is equal to 1, what is the OR gate operation? If any one of the input is equal to 1, automatically OR gate output goes to 1. So here the OR gate output is completely dependent upon the x1. If x1 is equal to 0, output is 0. If x1 is equal to 1, the output is equal to x1. Okay, so see here, the x1 completely followed to here and we are giving it the first flip-flop input. Okay, the same operation will be done for x2, x3, x4 also. So when you are giving load value is equal to 1, first the OR gate output is equal to here x1 and here x2 and here x3 and here we have x4. Okay, so here totally, see here is very simple thing. Whenever load is equal to 1, I have connected the circuit diagram and the x1 is went to the D flip-flop input. Okay, so at that time you have to give the clock input. So whenever the clock input you have given, automatically the x1 value is present at the output place. Present at the output place. So this is the load is equal to 1 operation. So next, load is equal to 0 operation. Now we will see load is equal to 0 operation. Right. So whenever load is equal to 0, this NOT gate output goes to 1 and this load value is equal to 0, load bar value is equal to 1. So the load signal is connected to the blue color AND gates. Now this 1 is connected to the, that is load bar is connected to the pink color AND gates. So this 0 is connected to this all blue color AND gates. Now these AND gates are not in working condition. That means the blue color AND gates are in not working condition. That means the output of this blue color AND gates are 0, 0, 0 and 0. Right? Now the decision is completely depends on the pink color indicates. So one of the input of the indicate, pink color indicates are 1. Okay, 5, 6, 7, 8. Right. Now the another input for this indicate, the another input is equal to Q. Here also the another input is equal to Q. Right? So here the another input is equal to Q. So like that, the first indicate, one of the input is equal to first flip-flop output. The second indicate input is equal to second flip-flop output. The third indicate input is equal to third flip-flop output. The fourth indicate input is equal to fourth flip-flop output. Okay, right. Now here the data, here the Q1 will be there. So now here the value is equal to Q1. This is the value is equal to Q2. This is Q3 and this is Q4. Okay, so this is the another input. Here one input of the pink color indicates 5, 6, 7, 8 indicates input is equal to 1 and another one is equal to Q1, Q2, Q3, Q4. Like that here we have. Okay, right. Now if Q1 is equal to 0, the AND gate output is equal to 0. If Q1 is equal to 1, the output is equal to 1. So then here the output is equal to Q1. It may be 0 or 1, whatever it may be. If it is Q1, automatically output is Q1. If it is 0, output 0. If it is 1, output is 1. So we know that the OR gate output is equal to here Q1, this is Q2 and this is Q3 and this is Q4 and this is Q4. So this is the load is equal to 0 combination. So when the load is equal to 0 condition, the flip-flop input is equal to the previous output of the same flip-flop. The same flip-flop output we are connecting to the as in a input. Okay, so this is the load bar is equal to load bar condition. When it is going to 1, then that is the situation. That is, it is very simple. Load is equal to 0, then it working as an previous output is connected to the same output. There is no change in the output. So whenever the load is equal to 1, it will take the data, whatever it may be available at the x1, x2, x3, x4. The same data is shifting to here. Okay, so once again, see here, it is very simple operation. Here we have AND and OR logic. This logic is helps to process the data. So this AND gates, blue color AND gates takes the parallel data, that is x1, x2, x3, 4 to the flip-flop, and this pink color data is taking the same flip-flop output to the next state input. So this is the controlled buffer register. So when you are giving the load command, then only it will takes the input data and loads to the register. So when you are giving the 0, it is not taking the input data. The same previous output data is following. Load means loading the data from somewhere. Load bar means we are not loading the data from somewhere. The previous data is following as is. So this is the working of the controlled buffer register. Okay, this is the working of the controlled buffer register. In the next video, we will see shift registers concept. Okay, thank you.